That's a short video on spatial autocorrelation by Laura, Stephen, and Jonathan. So Tober's first law of geography states that everything is related to everything else, but things that are near one another are more closely related than distant things. Autocorrelation literally means that a variable is correlated with itself. Pairs of subjects that are close to each other are more likely to be related and have values that are similar, and then pairs of phenomena far apart are more likely to have values that are less similar. Now, when you throw the spatial component in with our autocorrelation, you can see how patterns are distributed through space and the likelihood of correlation based on their similar variables or values. When we have a positive spatial autocorrelation, it may become possible to predict values of a location based on values from a nearby sample. Geospatial scientists use spatial autocorrelation to test whether or not the frequency distribution of the values is influenced by the space around them. Usually using values ranging from -1 to +1, they can determine that if some phenomenon have a negative correlation and show a dispersed distribution versus a positive one, which will show a positive correlation representing a clustered distribution. So in essence, we use spatial autocorrelation to understand the degree to which one object is similar to other nearby objects. When you're faced with spatial autocorrelation, it is important to run statistical tests. You want to run these so you can see if there's a positive, negative, or if there's a relationship, or if there's a zero relationship. Some examples of tests you may want to run are ordinary least squares regressions or geographically weighted regressions to determine how well your model will predict future phenomena. Example of applications that are spatially autocorrelated in the geospatial realm include whether burglaries are concentrated in a certain area of the city, if 911 calls are concentrated in a certain area of the city. You can study the relationship of plant and animal communities and variables around them. You can also analyze changes in spatial distribution patterns of population density at regional or even local levels. This is an example of an average family size map for Virginia, and we see up here in northern Virginia, there's a clustering of larger average family size, and this is something that we can expect based on our knowledge of a higher population in that area. These are the actual results from the Moran's eye test, and it shows that in fact it's clustering, and based on the Moran's index of 0.73 and the z-score of 8, there's pretty high correlation that this is clustered, and that they're pretty much without a chance. There's no way it can be anything other than clustered.